Hi, sorry to cut across. I don't know if you can hear me. There's no audio from the lecture room. Uh, sorry to. Um,
Okay, thanks, Martin.
For the best.
Yeah. Oh, something's happening. No, that's better not.
This one. This one.
Yeah. No, that's helpful.
This, if we keep back on this microphone, so I can't leave it on.
On this, we can switch this off.
Sorry?
um, sorry, yeah, I just hopefully it's not an issue. I was just worried maybe if the recording on Zoom mightn't pick up the audio for the talk. Um,
In this one on. Can you hear us now?
yeah, that's grand. Yeah, there's a slight echo, but it's no
Okay.
issue.
All right.
Thank you. Sorry about that.
Oh, we tried about it. So I'm going to start with some probability. No. I'm not sure that the echoes coming from. In fact, this bit of probability theory you can also find it by work on statistical mechanics. So, if we have a sequence x1, x2, just the sample that to minimum volume probably relay itself.
By that?
Try this one. Like that? No echo. That seems like it might work. Can it still hear us? Can you still hear us? Martin?
Yeah, that's good. That's perfect.
Lot of sound.
Yeah, and I suppose sorry, I'm just nitpicking just I think the
Can you hear
board.
us, Martin? Try saying
Yeah,
something.
Um, the board to the left. I don't think the board on the right's being picked up on the recording.
The only way that was for that.
I think it was the laptop that was playing. I don't.
You have to give the sound a warning, but just.
Yeah.
We do the best we can. I'll try putting sound up on this one. Can you hear us, Martin?
Yeah, that's perfect.
Okay, I can hear you, then that's fine. Let me just try working it this way. All right, we can hear you. You can hear Tony, hopefully.
All right. Okay, so if we have a sequence of random variables which are identically distributed random variables. Then the weak law is well known. So, for example, if these are throws of the dice, then they have equal probability, so they are identically distributed and independent. So IID. And then it's well known that the probability that if you take the sum of an xi, I is 1 to n, divided by n, so the average, then that converges to the mean. So the expectation, all right, of xi, which is independent because they're identical, the expectation is independent of I. And so this less than epsilon tends to. So with probability 1, the average that you take is close to the expected value. So the expected value is 3.5 if you have dice, and because each occurs with probability 1/6, and if you throw many times, then you come close to that. This is proved using the Chebyshev inequality. Namely, the probability. So now, first of all, you can see that the expectation of x is contained for each I, and I can take the difference. So I might as well assume that the expectation is 0, because I can always subtract that from x1. So now the probability of 1/n from xi. So I take the expectation 0, greater than epsilon, is less than. So this is the same as let me write that as an integral. The integral x d nu x from right, so from minus epsilon goes epsilon and in fact where mu n is the probability distribution of this, but because they're independent, it's a product. So we can write this as the integral of 1/n sum xi. I should write this. So we can write this also as the integral. So I write here the square, and then you also the square. And then it's from x epsilon squared to infinity, and then the probability of x squared nu n units, where nu n is the probability distribution of the average. But this is a product distribution, so we can write this as the integral of 1/n times the sum of the xi, and then the product, the probability of xi, I is 1, n, where the nu does not depend on I squared again. And from epsilon squared to infinity. Now we use Chebyshev's inequality. This is less than. So in this is greater than epsilon squared. So
What's the difference between nu and nu? And what is nu?
yeah, so nu n is the distribution of this thing. And that's a product distribution of the xi's. Okay, this is a small xi.
Well, then why is it no n on that?
So there's no n on this because nu is the distribution of xi,
And they're identical.
and they are.
You can just tell us this, we wouldn't need to. Well, you did, a couple of times.
He did tell us already, but he's writing it out now.
So now I write out the square, and I get 1 over n squared times the integral, and then the sum of the xi's. But I've assumed that the expectation of xi is 0, so the integral of xi, unit xi, is 0. So in the square, all that remains is the xi squares. So this is a sum. I is 1 to n, and then the integral of xi squared mu xi. And again, provided that epsilon squared is greater than. So if I now write, so this thing here is greater or equal epsilon squared. So it is less than 1 over epsilon squared of that. And now if I assume that this is finite, then one of the n's cancels and we're left with 1 n underneath, and so that tends to 0. So this is the proof of the weak law. This is called so-called weak law. But one can actually prove something a little bit better, namely that this actually, the so-called strong law says that this actually happens with probability 1. The limit goes with probability 1. So that says that the probability that the limit of 1 over n sum xi, so now is equal to b, but we put the equal to 0, is 1.
How do you get from a multi-dimensional equal with the product of new xi's to a sum of one dimension?
So the sum of the xi squared is the sum over xi squared plus the sum I lambda and j twice xi xj.
Yeah, as a measure, you get a product of u's there.
And here you get a product of xi and xj, which is 0.
Yes.
So then you have only less than
Yeah.
left with
As
the
a
sum
measure,
of the
you've got
xi.
product from I is equal to 1 to n new xi. That's a multi-dimensional integral.
Yes, but all the rest is not. It's a probability. These are probability measures, so the probability of the rest is 1. Because there's nothing there.
So you're doing all those other integral and just getting 1.
Yeah.
Now, there is a strong law which says that not only does it come arbitrarily close, but it actually has the limit equal to 0 with probability 1. So that means that if you take a large enough sample, then
That's
any
the thing 0.
yeah, that's because I take otherwise, of course, you have to subtract that here again.
But that's just the redefinition of
Yeah, that's just the redefinition base. That's no problem. Now, this is proved using the so-called well, I can't tell you that, but And that says that if xi are I reading random variables. Well, actually, that's not really necessary. The probability, the sum of the probabilities, the really events. So let me write. Is sequence is an event that so I shouldn't really have independent events, but I'll write it straight away in terms of example. So this is the probability. So say k is the 1 over k. So x I 1 k is greater than epsilon. Then here probability, the sum of the probability of anything fine, right? Then the probability of the intersection n is 1 to infinity of the union k greater to equal n of anything is 0. So this says that the tail then is 0. And now I apply, so this holds for any independent events, but I take this particular event. And if you take this particular event, then you find that if the probability of the sum of the probabilities is finite, then this holds. So now you compute the sum of the probabilities in this case, and you find it the same way as here, that's finite. And if you have that, then so I won't go into that, but there's an assumption there which. So if we assume, so here we use the square, and here it's easiest to use the quarter. So we need to assume that the expectation of xi to the 4th is 5. Now, in fact, that is not needed, but I won't go into that.
Can you say again what you mean? You will any intersection of this?
Yeah, so the AK is an event, so
Yes.
that's the
I have those.
the values of the omega, if you like, such that this holds. And then you take the union for k greater or equal n of such events. So that means that this holds for large k.
Yes.
And then you take the intersection, so it holds arbitrary large k.
An infinite intersection, that requires.
Yes, this is the infinite. It's k from n to infinity. Yes, it holds for some large k, and then arbitrary large. And the probability that that is so is 0. And well, to do that, you do a similar thing to here with the Chebyshev inequality, but to the 4th power. And when you do the 4th power, then you get a 1 over. So here you've got 1 over n. But for the sum to be finite, you need 1 over n squared. And that's why you use the 4th power. If you do the 4th power, you get a 1 over n squared. And you get this to be 0. And then, what does this mean? Now, I put n to be, so n epsilon, because there's still this epsilon, to be this set. So the intersection of the union k. Not visible.
Yeah.
So this set is n. And then if you're outside this set, so if you're not in this set, then that means that the sum here is less or equal to epsilon for n large enough. So for large enough n, then this is less than epsilon. And since that holds for all, you can say that the lim sub, so if omega is not in n epsilon, then the lim sub of the 1 over k sum xi is less than or equal to epsilon.
Sorry, could you just remind me what lim sub means?
The lim sum is you take the supremum of this thing for large enough k. So you take, it's precisely this. You take the supremum of this quantity, and then you take the supremum over larger and larger n. So you take the supremum over the tail, and then you shift the tail to infinity. And if the lim sub is 0, then the limit is 0, because the lim inf is automatically greater or equal to.
What's omega? What's omega?
Little omega.
The omega is that's the space in which the random variable lives. So you know a measure is defined on the space omega with an algebra, sigma algebra. So these are subsets of omega on which the measure is defined. You know.
But then what's little omega?
Yeah, so little omega is an element of both. And n, this n epsilon is a subset of omega, and because of this, it has measure 0. And now this holds for epsilon, but it holds for all epsilon. So if I now take epsilon to be 1 over p with p integer, then I can define n to be the union of the n 1 over p for p integer, and then this is still a set of measure 0 because it's a countable union, and the probability of a countable union is less than the sum of the probabilities, which is 4 0. So for this n, then it's less than every epsilon, so it's 0. So that's a bit of probability for you, and I'm not done yet. I need one more thing. And that's the central link, you know. And that says that, again, with such a sequence of independent random variables, the probability that 1 over n from r is gone to n, but now square root n of xi. And I'll take again expectation equal to 0. And this to be an interval a b converges, and then to infinity, of course, to the Gaussian distribution. So that's 1 over root 2 pi sigma squared integral a to b of e to the minus x squared over 2 sigma squared. The x where sigma, well, squared is the expectation of x squared. And I need to tell you also how this is proved. And that follows from a theorem which I will not prove, namely that define if mu is the measure, or look at the measure, and define the integral of e to the I Tx mu x is phi mu x, phi mu t is the so-called characteristic function. And now the theorem says that if you have a sequence u, if nu n is a sequence of probability measures, then if and well maybe say and phi nu n t converges to phi nu t for all t, then nu n converges to nu, and the measures converge. Now this is basically Fourier transformation. So I won't prove this, but you basically use the inverse Fourier transformation theorem. Now, of course, that holds for L2 functions, and this is measures, so you have to do some work to show that it's true, but I won't do that. So, this is a well-known result in probability theory that if the characteristic functions converge for every t, then the measures converge. You see that the measures converging means something like this, that if you take an interval, then the probability is given by converges to the probability of that interval. So let me leave it at that. Now, once you've got this,
I'm still confused. Previously, I thought nu n was took many arguments. It was multidimensional. And u is one dimensional.
yeah. So now this is nothing from the previous parts. This nu n is just any sequence of probability measures on the real line.
Oh,
It
it was one
also
argument.
It also more general.
With one argument, is that correct?
This one.
Previously it was multidimensional.
Now this is over R.
You say it's simple for two different things.
Yes, sorry, it's two different ideas. Now, once you've got this, it's very easy because you just compute the characteristic function of this variable. And when you compute the characteristic function of this variable, you can use that. So the exponential becomes a product of exponentials, and the integral becomes just a product of integrals, and you just do a little bit of limiting theory, and you find that what you get in the limit is always the characteristic function of this one, which itself is also Gaussian. Of course, the Fourier transform of Gaussian is a Gaussian. So that's very easy to do. Okay, so now I've got the background. Now let me get back to what the Wigner did. Maybe I do. So Wigner considered Hamiltonians HM. And for simplicity, I do the same assumption as he did with his first paper. Then he wrote a second. In the first paper, it's very specific. I won't be quite as specific as that. But on the other hand, in the second paper, which is only 1.5 pages long, he claims that actually it holds very general. Well, yeah, we'll see. But in the first paper, he has very specific Hamiltonian, namely each of these entries was just plus or minus 1 with probability enough. Well, I won't be quite that. So this is 1, 2, H. 1 on n, h, n minus 1, and etc. And of course, it's symmetric, so a is h j r. So we assume now that the h hij I less than j are I random variables with distribution mu, which is a probability measure, also distribution given by the probability measure mu, which we assume to be symmetric, so such that mu of minus the second with respect to the mu vector. And that means in particular that the integral, so that's the expectation of x to the 2n minus 1 mu x. So that's the expectation of odd powers are all 0, because this is an odd function and the measure is e. Right, so that makes it a little easier. And so this is similar to this, but more precise, because all the odd powers are 0. And now he looks at the distribution of the eigenvalues.
Why is the Hamiltonian 0 but I
Yeah, that's for simplicity. So he did that as well. I don't think you need to do it, but I've assumed it as well. If you don't do that, it makes the argument more difficult. So it's easier, but I don't think it's necessary. But other things are a bit more complicated. So now he looks at the distribution of eigenvalues, and he wants to show, at least that's what I understood from him, that the distribution of eigenvalues converges to some limit as n becomes 1 to 1. Now that's obviously not the case, and he doesn't claim that either. Because the bigger the matrix becomes, of course, the bigger the eigenvalues become. So instead of looking at Hn, we have to normalize a little bit to scale it. Now, in his paper, the scaling is very unclear, but I figured out what it means. So the eigenvalues, we have to do the same as in what I just erased, the essential limit theorem. So we want to look at the eigenvalues of 1 over root n, Hn. So the measure.
Sorry,
let me first
excuse me, could we
introduce
with the
what
camera?
introduces, that is that Sn the distribution function that is Snx if the number is the fraction of the eigenvalues of 1 over root n Hn less than or equal now this is called the distribution function in probability theory because you can associate a measure with that. So the associated measure is mu n. So this is not mu, here's mu. But this is the measure nu n. That's the distribution of the eigenvalues. And so it satisfies S m x is the measure of the set from minus infinity to x. And so the new n's are just the eigenvalues of hn. So nu n of minus infinity, the x, if you like, is given by 1 over n. Remember that the total number of eigenvalues is n, so the fraction we have to divide by n. And then a sum over the eigenvalues. So that's the elements of the spectrum of hn divided by root n. And then there may be
What do you define here? Sn is defined, I understand that, right?
fraction of the eigenvalues
Yeah,
below x.
Yeah.
And the measure is given by the corresponding measure to this distribution.
Then if I know what Sn is, then I look at the right hand side. Is that meant to be a definition of UN?
Yes, it could be, because the probability distribution on the real line is uniquely defined by its distribution. So you see, I'll draw a picture in a minute. First, let me write this form. So this lambda in the spectrum could have more than one eigenfunction. So it could be degenerate, and that is measured by the trait of the corresponding probability projection. So part P lambda is the projection onto lambda, and the trace of that is just the number of eigenvalues in the degeneracy. And then there is the delta on lambda. So delta lambda is Dirac's delta, which is actually a measure. It's not just a distribution, it's a measure. And so I can indicate that now in a picture. So if there are a few eigenvalues, so suppose these eigenvalues have some values, so then each eigenvalue so delta lambda is a measure which is defined, so delta lambda, sorry, this is nu n, so delta lambda of minus infinity in x. So that means this is 1 if lambda is less than x, and it is 0 if lambda is greater.
And are you assuming the eigenvalues are all positive?
No, this is the real line, so they can be either positive or negative. I didn't put any 0 in there. So delta lambda of say A is simply 1 if lambda is in A, and 0 if lambda is not in A. And that's the same as Dirac's delta. And so you see, I can indicate the nu here by delta functions, so they're all stripes like that. And then, so some are closer together, some are further away. And what is Sn? Well, Sn, you can, so then I have to count the number here. I have to divide by n. So it is 0 here, then it steps up here by 1 over n. Then it steps up here by 1 over n. Well, and you see the picture, and it ends at 1. So Sn is, of course, an increasing function, and it increases from 0 to 1, like a distribution function should do. So this is the corresponding measure. All right, so now what do we want to prove? So we want to prove that mu n, which depends on n, as n increases, converges to some distribution nu, which I don't know yet. That's going to be Wigner's distribution, of course. But remember that these nu n's depend on probability. These are measures, but they're measures on the real line. And they depend on what the h's are, right? Because it depends on what the spectrum is. And this spectrum is random. So these measures are random measures. So nu n is a random measure. And so what we would really like to prove is that this random measure converges to a fixed measure, which is not random, with probability 1. Because if that's the case, then whatever sample you take, just like in the case of independent random variables, no matter what sample you take, almost certainly, if n is large enough, it will have almost this distribution. So that would be a useful result, but it's not something that Wigner proved. And so I've set out to prove that, and it is not easy. And so I don't know if somebody else has already done that, and under what conditions. But that didn't hold me back. So let me now show you a little bit of how this works. So first of all, you expect then, of course, mu is going to be the limit of the expected value of mu n, mu factor n. So the first thing is to look at the expected value of mu n. And that is something that Wigner did. And let me show you how that is done. Well, to prove that this is so, we look at the expectation of mu n, and obviously that is also a probability measure. That is the average of probability measures under this averaging process. And that's also a probability measure. And to show that this converges, so the expectations converge, we can look at the characteristic functions. So it's similar to the central limit theorem, but it's more complicated. And why is it more complicated? Because in the central limit theorem, the distributions of the nu n's were independent, and now they're not independent. The h's are independent, but that doesn't mean that the eigenvalues are independent. And so that's the difficulty here. So let's write down the characteristic function phi of t. So that's the integral e with the I t lambda mu n lambda. Now I can insert that formula. So that's 1 over n. And then we have a sum over lambda in the spectrum of 8n divided by n. And then e to the I t lambda times the trace of p lambda. Like that. But this, by the spectral formula, can be written as 1 over n times the trace. So we can put the trace outside, and that is e to the I t hn over root n. And so we would like to show, in the first instance, that the expectation of this converges. And for that, I'm going to do a perturbation expansion. So I'm writing this as 1 over n, and to infinity, and then 1 over n factorial, I t over n over root n to the n, and then the trace of h n the little n and big n not to be confused. Right? And so we're looking at the trace of the nth power of h, much easier than e to the ith. The trouble is, when you write such a perturbation expansion, you need to know that it converges. And, well, in his first paper, Wigner had that the h to the power n, the h's were all bounded because he had a bounded distribution. In fact, he had plus minus 1. If it's bounded, then it's obvious that the trace is also bounded, so then there's no problem. If it is not, well, then there's problems. Then you have to show that this converges, and I'll go into that a little bit later. In any case, for finite n, if it's bounded, then it converges.
Can I ask a question? Is nu n a monotonic vacancy function?
Nu n is not a function, it's a measure. Nu n, this is a measure. So you can write this if you like. You can write
Eigenvalue below value x.
and now this
I thought nu n was an eigenvalue below value x. I thought nu n is defined as a number of eigenvalues below value x.
No, that's S. Nu n is the sum of this. Yeah, no, I just go there. But
I saw a line defined to
Nu n nu n was equal to what was sum of around the 20 they're not allowed.
there's no x anywhere.
No, they're just, these are delta measures, so that's the picture that I had with all the delta measures.
There was something about the number of eigenvalues below value x.
Yeah, so if you now take nu n from minus infinity to x, so the probability of the interval minus infinity to x, that's Sn. So this is the number of eigenvalues below x.
So is that the same nu n in those two equations?
This nu n is that nu n. So I have nu
So
n.
nu n depends on x.
But it's nice to put in
You can do it on that eight.
Yes.
something number.
So this is evaluated normal name.
When you
That's the
evaluate,
measure of the set. That's the probability of the set.
And then takes a set as its argument.
Now, then we need to compute these traces. And that's where it gets interesting. So that is not easy. So I'll do some example. So n is 2. Well, if I take n is 1, well, the trace of hn is obviously 0 because there was zeros on the diagram. So that's trivial. So we can start with n equals 2. Well, then the trace of hn squared is very simple. This is a sum I less than j, h, ij, h, j, I, and then twice.
I think you said that Hij is the same as
That's right. So this is square. And this is easy because the Hij's are independent random variables, so the squares as well. So we know straight away that this converges to twice the expectation of H power j squared, which is 2b squared.
That's the notation Wigner used.
So now, the expectation, these are all independent random variables. And so this converges to the average, the expected value. That's the theorem I had before in probability. But the trouble is, next, it's no longer so. So let's do ME4.
We're assuming the Hij's have expectation on this curve.
Yeah.
So these are variance, these are variances.
Yeah, so the measure is symmetric. So all odd powers have expectation measures. And so I don't need to look at the third power, it also is even. So in fact, we get that the trace, we get immediately that the trace of H n to the 2n minus 1 is equal. Right, so I look at the trace of Hn to power, just to give you an idea how that works. So now what terms do we get? So it is obviously equal to sum over I1 not equal I2, because the diagonals are 0. So not equal I3, not equal I4, not equal I1, because of the trace condition. H I1 I2, H I2 I3, H I3 I4, H I4 I1. And now I have to distinguish three cases. The first case is that they're all different. So that's a sum over I1, I4, all different. And then the same thing, and I won't drop that. It's a 0. That's going to be 0. Then there is plus. Now, then there's possibilities that they're equal. Now, we could have I1 equal to I3, we could have I2 equal to I4, or we could have both. Now, if I write down first, so now I1 not equal I2, not equal I3, not equal I1. So let's first assume that I1 and I3 are the same. Well, then it's better to call I4, I3. That's what I did here. And then we get H I1, I2, H I2, I1. Well, that's of course the square. And here the same. So this is 1, 4, 4, 1. So it's H I1, I3 squared. Now there's the other possibility that 2 equals 4, but you will see that that's the same. So I'll write it anyway. H. So if I2 is I4, then we get I2, I1, I2, H, I2, I3, H, I3, I2, H, I2, I1. And then finally, this case where both equalities hold. And so I'll just write down plus the sum H I j to the 4, I less than j. I think twice here. So now we need to take the expectation of this. And obviously, this one doesn't work. Now the expectation here, well, you can see that this term is actually the same as that term. because it's also two squares, so I can just rename I1 and I2. If I need to change I1 and I2, then it's the same. So we actually have twice this term, and then we have this term. Okay, so what do we get for the expectation? So here, these two are independent, and so I get two terms. So it's twice. And then we have a sigma squared and another sigma squared. So a v squared, another v squared, that's v to the 4. And then we need to count the number here. And that, of course, is n times n minus 1. So there's 3, n minus 2, n minus 2. So that's the expectation of this thing. But we also have the expectation of that one. So it's plus. There's also 2 there, but so this is n times n minus 1. And then here we get the expectation of the 4th power. I call it x4. So you see already that you need to know something. You need to know that x4 is finite. So you can't do this, and I said that already. You can't do this expansion unless you would know that all the powers have expectation finite, but it's not enough. So now, what happens if I take n to infinity? Well, I'm dividing here by n, and then n is 4, so I divide by another n squared. So that's n cubed. So you see that if I now divide by n cubed, then I have to divide by n cubed here, and here by n cubed. And then here we have only 2 powers of n, but we divide them by 3. So this converges to 2 v to the 4. And now, Wigner made a leap of faith and said, well, so probably this holds for all even powers. And so we get some coefficient of v to the n. So we conjecture that 1 over n to the m plus 1, and then the trace of hm to n converges to some constant which we call Tm times v to the 2n. But you see that we are neglecting here this x4 term, and the higher the power is, the worse you get. You get more and more, higher and higher correlations in there, and we have to control. Now, it is not difficult to see that the powers of n in front, and this is what he argued, that the powers in front of these higher expectations, they are always of order 1 over n, or 1 over n squared, or higher than that. So in the limit, they should vanish. But that's not good enough, because we've got a sum of them, and the larger n becomes, the larger coefficient you get in front. So we need to know better than that. But let me first show you how to compute this Tm, because that's quite nice. So computing Tm. So we want to. So how do we get these v to the 2m's? We get them when we all have only squares of h's. So we don't want any higher powers of h, which means that each pair of indices occurs precisely twice or not at all. Right? In this product, it occurs precisely twice or not at all. So we're going to associate with such a term a graph or path. So associate with a term, a path, which is constructed as follows. We start at 0 and we end at 2m, which is n. And now every time that, so every time that we get a new pair, we go up. And every time we get a pair that we had before, we go down. So we could go up, 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 down, 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 up, down, up, down, up, down.
Well, just do anything.
Right? And it's easy to see that all the terms are precisely characterized by this. And it's also easy to see that the number of terms that you can correspond with this is always of order n to the power m. So for example here, so let's go back here. What have we got here? We have two terms, and that's why I wrote them separately. So this term has, well, I didn't write this one, but it was I1, I2, I2, I1. So I go I1, I2, I2, I1, because I've had it. And then I have I1, I3, so that's a new one, and I3, I1. So this term corresponds to that. But this one goes up, up, down, down. So that's the other one. And of course, there's only 4. And
Isn't this going to be essentially Wick's theorem?
no, it's not Wick's theorem. It's a little bit more tricky. Because it's not Gaussian. It's no Gaussian behavior here. They're just random variables. The Wick's theorem holds for Gaussian variables, but here we don't have Gaussian variables. So basically, to obtain this coefficient here, we have two graphs, and that 2 corresponds with those 2 graphs. And so we want to count the number of such graphs. And I'm afraid there's a lot of counting involved, which I won't have time for, but I'd like to do this at least, which Wigner did, but a bit more awkwardly. So what do we want to count? We want to count the number of paths. You can see it as a path. The number of paths of this shape which go from 0 to 0. So at the ends it must be 0. That's because of the periodic boundary conditions, the trace. And then it must never go below 0. Because if it goes below 0, then we have, for example, here, then we have more repeats than we can have, because there's only so many. So we must remain above 0. So how do we count that? Well, first of all, the total number of graphs from 0 to 0 is easily seen to be, so the number of graphs path is equal to the number of paths, the general paths from 0 to 0, minus the number of paths going below 0. Now, what's the number of paths from 0 to 0? So then I can go like that. Well, then you just count the number of, every time you either go up or down. So, and you must have exactly n going up and n going down. So you just choose the n, you choose the n that's going up out of the 2n. So the first one is easily seen to be 2n, choose n. Now what about the other one? Well, let's look at this graph. How can we count those graphs that go down below 0? Well, if they go below 0, then they're certainly somewhere -1. And what I'm doing now is I'm going to take a reflection. This is the reflection trick that is also used in Brown's motion. But I realized that only afterwards. So what I'm going to do is I'm going to now, from this point onwards, I'm going to just reflect up. So instead of this one, I get that one. And you can see that if you do that, so this is 0 on this one. If you do that, you get a path which ends here now at -2. So this is 0, you reflect along -1, so it ends at -2. But you can easily see that all the paths that go to -2 from 0 are obtained that way, because you can always reflect back. So it's just a bijection. And the number of paths that end at -2 is also easily seen in the same way. So this is -2m, choose M-1. And this can be written as 2m factorial divided by m factorial times m plus 1 factorial. This is the answer that Wigner had, but it's much easier to derive this one. So now let me write down what the characteristic function then is going to be. So assuming that this always holds, and so it converges to, and I'll have to end there, but that's where only my work started. So the 1 over n to the m plus 1 times this trace converges to Tm times V. So this converges to a sum. M is 0 to infinity. 1 over 2m factorial. And then minus t squared to the m. And then V to the 2m, and then Tm. But Tm we've got there, so we can divide out the 2m factorial, and we get 1 over m factorial, m plus 1 factorial. And this, well, is fairly easy to see to be a Bessel function. And to be precise, it is the first Bessel function. And the argument is, well, actually 2, because in the Bessel function you have t squared over 4. So it is 2 tv. So it's t squared and v squared to the n. But divided by, that starts with z. So we have to divide by TV. Okay, now, if you now write down, I don't have time. If you write down an integral representation for the Bessel function here, then you can transform it so that the TV drops out. And when you do that, you get, this shape. where this measure is now explicit. So new,
Without the
yeah, there's no n now. So that's the limit of this. And that's again, so that means that this characteristic function converges to the characteristic function of this random variable mu. If we find the characteristic function that corresponds to this. And that's done by doing an integral representation of this and doing some transformations which I haven't got time for. And so what you get is that this is, let me see, it is 1 over pi v, and then the square root of 1 minus x squared over 4 v squared v dx. So this is a semicircle distribution. Of course, we must assume that lambda is negatively equal to b, not 2b. So it's a circle distribution like that, minus 2b. That is his semicircle distribution. And you see that, now I don't have time to go any further, but if you want to deal with all the remainder terms here, then you need to deal with the x4, 6, 8, etc. And then all these terms come into play as well. Well, then this here is only this term, but the further you go, the more terms you get. And you need to get an estimate of the possible contributions of that. And for that, you can still use paths. So then you get paths, but they don't necessarily enter 0. And then you have to count, so there's a lot of counting involved, the number of possibilities of getting, say, x4. So you could get x4 v to the 2n minus 2, or something like that. Or 2n minus 4. But you get all sorts of terms. You get also x4 squared, and you get x6 and x8, and all those you get. And you need to count how many of those you get. And that must not be so big that it overwhelms the 1 over 2n factorial that you've got, the 1 over n, which is 1 over 2n factorial. Now I've got such an estimate, but that's a lot of work here. And that is not enough. So for the moment, all I've done is look at the expectation. So, oh, that's not gone as well. The expectation of mu n. But we want that mu n almost sure. So we want to look at the expectation of the square, and that will be proportional to 1 over n squared. So the Borel-Cantelli lemma will apply, provided you can estimate again the coefficients of 1 over n squared for different n's. There's also higher powers of n, but really, what matters is how it behaves with the little. One more remark. So you see that this distribution here is bounded. Now, of course, initially it's not bounded. Well, it is bounded if we assume that Hn is bounded. Then it's bounded, but it's not necessarily bounded by this. So that's not even obvious either. If you take a Gaussian distribution, then even the x2m are not bounded. So then you have to take that into account as well. So you get a Gaussian distribution initially, which looks like that. And you have to imagine that then the tails disappear. That the tails disappear is not obvious. And so far, I have not been able to do the estimates beyond Gaussian. And I suspect that maybe it doesn't hold.
Well, I mean, the tails disappear.
Yes.
Is it a full distribution?
The distribution, so there could be remnants here.
But that's the tails. That's the.
That's it. Yeah, so if the distribution initially of the h's is
Tracy-Witham distribution is they're given by the Tracy-Witham distribution, the tail.
if the distribution of the tails is particularly wide, then you cannot expect it to go to a finite value set. So that's itself a bigger problem.
That's very subtle there. Okay.
So even if you have a distribution that's exponential, well, it might hold, but this proof won't do it. I don't think by expanding it will do it. Now, in the case of the central limit theorem, we didn't have to do an expansion. We did the expansion inside the power of n. But here, it's not so obvious how you would do that. So you'd have to deal with this straight away. And I don't know how to estimate that. The problem is that this Bessel function is not so easily written as a product. If you could write that as a product, then maybe you could write this as a product. I don't know. I can't see how that's really done. So all I did was counting. Lots of counting.
That's a very new exposition. Questions?
Did you do some experimentation to see if, when you try something that looks like it's never going to work, maybe from your estimates, it will still converge to this?
I have not done any computing this directly, experimentally. That is, take some distribution, take some random, and see what happens. Now I haven't done that. What I have been doing is mostly counting, and for that I do a lot of experimentation as well, because I have to look at what cases are available, or what cases can you have, and how many of those.
I understand, but because you somehow are getting a lot of mileage out of the independence of the variables, right? Because all the off time.
Yes, unfortunately, not enough. Yeah, so I can't tell you whether it would still hold for this distribution, the exponential.
That's a very simple thing to try and check. Short
For me, the estimate here will not work, because then basically what I get is a 2n factorial up above as well. So then there's nothing left, because this has to hold for all t's. It has to hold for all t. And so you can't just do it for small t. That's not good.
I would stop the recording, maybe just.